Welcome to day 16 of our low-level design course. Today we are going to explore two important structural design patterns, the Facade pattern and the Flyweight pattern. These patterns are key in solving real-world software design challenges. The Facade pattern helps in simplifying complex systems by providing a unified interface, while the Flyweight pattern is designed to optimize memory usage by sharing common data across similar objects. So let's dive in and understand how these patterns work and when to use them efficiently. By the end of today's session, you will have a solid understanding of these two design patterns. We will explore the Facade pattern, which is used to create a simple interface for complex subsystems, and the Flyweight pattern, which helps in reducing memory usage by sharing common data. We will also look at practical applications, discuss UML diagrams, review code examples, and work through some hands-on exercises to solidify your understanding. Before we jump into today's topic, let's quickly recap what we mean by structural patterns. Design patterns deal with the composition of classes or objects. They are concerned with how the system's components fit together. The key idea here is composition over inheritance. That is, how we can compose objects and classes in a flexible way to create more complex structures. The two patterns we will cover today, Facade and Flyweight, are perfect examples of how structural patterns can improve system design by making it simpler, more maintainable, and efficient. Let's start with the Facade pattern. Imagine you are interacting with a complex system, but all you need is a simple interface to get your work done. That's exactly what the Facade pattern provides. It defines a high-level interface that makes a subsystem easier to use by hiding its complexities. The Facade does not modify the subsystem, it just makes it easier for the client to interact with it. This pattern is particularly useful in large applications with multiple subsystems where you want to reduce the dependency between subsystems and client code. So why do we use the Facade pattern? The main reason is to simplify the interactions between the client and the subsystem. Without the Facade, the client would need to interact with multiple complex subsystems directly, which can be overwhelming. The Facade provides a simplified interface and hides the complexities of the subsystem, reducing the learning curve for a new developer and simplifying code maintenance. It also helps in reducing tight coupling as the client is no longer directly aware of the subsystems it interacts with. Let's now look at some real-world examples of the Facade pattern to understand how it works in practice. One classic example is a restaurant. As a customer, you don't need to know how the kitchen operates, what equipment is used, or how the food is prepared. All you need to do is place an order with the waiter, who acts as a Facade, providing a simple interface to the entire restaurant experience. Similarly, in a computer startup process, you press a single button and the operating system takes care of all the complex background processes like loading the OS, initializing drivers, and launching startup applications. Now let's take a look at the UML diagram of the Facade pattern. In this diagram, you will see that the Facade class provides a simplified interface to the client. The client communicates only with the Facade, which in turn interacts with the various subsystems represented as separate classes in the diagram. The subsystems themselves are hidden from the client, making the system easier to use and maintain. Notice that the client is aware of the complexities of the subsystems, which is the primary benefit of the Facade pattern. Here's a practical example. Let's say we are designing a home theater system. Without a Facade, you would have to interact with various components like the DVD player, projector, speakers, and lights individually. But with the Facade pattern, you could create a simple method called watch movie in the home theater Facade class. This method would internally handle the interactions with all the subsystems, turning on the projector, dimming the lights, and starting the DVD player, all with a single call from the client. This greatly simplifies the client code and reduces the number of dependencies. Like all design patterns, the Facade pattern has both pros and cons. The key advantages are its ability to simplify the client code by providing a single point of interaction and reducing the coupling between subsystems. However, the Facade can also hide powerful subsystem features that may be useful to advanced users. Furthermore, a God Facade may emerge if too many responsibilities are handled by the Facade class, making it difficult to maintain and modify. It's important to find a balance and keep the Facade focused on simplifying the core interactions, not handling everything. Moving on to the flyweight pattern. This pattern is all about optimizing memory usage when dealing with large numbers of similar objects. Instead of creating new objects for every instance, the flyweight pattern encourages the use of shared objects. These objects share common data, while unique data specific to each object is stored externally. This can significantly reduce memory consumption and improve performance, especially in applications with large datasets or systems that create a lot of similar objects. So, why should we use the flyweight pattern? The primary benefit is memory optimization. Imagine a game with thousands of objects like trees, rocks, and buildings. If each object had its own unique data, the memory consumption would be massive. With flyweight, you can share common data across objects and store only the differences externally, drastically reducing memory usage. This pattern is particularly useful in graphics-heavy applications or large-scale systems where many objects are created with similar properties. Let's take a look at a couple of real-world examples where the flyweight pattern is used effectively. In a word processor, each character could be a separate object. Instead of storing the same font and style information for every character, the flyweight pattern allows all characters of the same font to share the font data, saving memory. Another example is in gaming, where many objects like trees and rocks share common characteristics like type or color, but differ in their position. These shared properties are managed by the flyweight, ensuring memory efficiency. Here's a UML diagram illustrating the flyweight pattern. The flyweight interface is the core of this pattern and defines the shared methods that all flyweight objects must implement. Each flyweight object stores only the shared intrinsic state. The extrinsic state, which varies for each object, is passed in by the client. This allows multiple objects to share the same flyweight data while maintaining their unique state externally. Let's look at a code example for the flyweight pattern. Imagine a chess game where each piece, like a king, queen, or pawn, has certain shared properties like color and type. These shared properties would be managed by the flyweight factory class, which ensures that only one object exists for each unique combination of shared properties. The position of the pieces on the board is the extrinsic state, and it can be passed in dynamically when needed. The flyweight pattern has several advantages. It significantly reduces memory usage, especially when dealing with large numbers of similar objects. However, it also introduces some complexity, particularly in managing the extrinsic state and ensuring that the correct shared objects are used. If not implemented carefully, the flyweight pattern can lead to code complexity and performance overhead in managing the object pool. Now let's move on to some hands-on mini exercises to apply what we have learned. For the Facade pattern, I would like you to design an online shopping checkout system. The Facade will simplify the interactions between subsystems like payment, inventory, and shipping. For the Flyweight pattern, design a shape drawing app where different shapes like circles and squares share properties like color and type, while each shape's position and size are unique. Let's summarize the key takeaways from today's lesson. The Facade pattern simplifies complex systems by providing a unified interface, hiding the internal complexity from the client. The flyweight pattern optimizes memory usage by sharing common data object, which is especially useful when working with large numbers of similar objects. Both patterns help reduce complexity and improve efficiency, but must be used carefully to avoid introducing additional challenges. Your homework for today is to design systems using three patterns. For the Facade pattern, design a travel booking system that integrates flights, hotels, and car rentals under a simple unified interface. For the Flyweight pattern, design a chess game where the pieces share data like color and type but differ in their position. Remember to keep things simple and apply the principles we discussed today. Before we end, here's a bonus insight. You will often find that the Facade and Flyweight patterns can be used together. For instance, in a game engine, the Facade could simplify interactions with various subsystems such as rendering, input, and sound, while the Flyweight pattern could be used to manage shared objects like terrain tiles, enemies, or characters, reducing memory usage and improving performance. Thank you for joining today's session. We have covered two essential design patterns, the Facade pattern and the Flyweight pattern, and explored how they simplify complex systems and optimize memory usage. Keep practicing these patterns and start implementing them in your own project. I look forward to seeing your designs and discussing them in our next session.